Just looking into what we have with the remaining items in your ALEKS Test 3 review. And we have just kind of starting off, and we have going back to what we have with quadratic functions. Okay, and we have with the first item. Okay, so we have the function that is quadratic and is presented in standard form. And regarding the minimum and maximum values, okay, we're looking at converting this function in terms of the vertex form. Okay, so right now we got f of x. Okay, we have is equal to negative 2x squared plus 16x minus 36 and again transitioning from the standard form to the vertex form. Okay, so I'll be looking at separating the variable terms apart from the constant at the end. Okay, so looking at what we have, so we have f of x and putting in parentheses, okay, negative 2x squared plus 16x and followed by negative 36. And I want to set the stage for the completion of the square. So what I'm going to do here is to ensure that I have x squared as the first term inside the parentheses, I'm going to factor out negative 2 and factoring out negative 2. So negative 2 goes into negative x squared times, and negative 2 into positive 16x, okay, that would be negative 8x. Again, we have followed by negative 36. Okay, now so I have the stage set where I can perform the completion of the square. So the first term inside the parentheses again is x squared. And to complete the square, I look at the first order x term inside, and we have the coefficient minus 8. And if I take half of negative 8, okay, so negative 8 over 2 will be negative 4. And squaring negative 4 would come out to positive 16. Okay, and the 16 will be used to form a square trinomial inside the parentheses. Okay, so we have f of x is equal to, okay, now we got negative 2 times the quantity of x squared minus 8x plus 16 and minus 36, okay, again to be the constant at the end at the moment. Okay, but for what we have going from the standard form to the vertex form, okay, so having completed the square, okay, so I got 16 that was added. Okay, so I have a square trinomial, but as I'm adding 16 within the parentheses, what I'm doing in the overall picture is adding not 16 but negative 2 times 16. So for what I have in this case, for the activity that I have collectively going on at the front, okay, so you got negative 2 times 16, so we actually have the subtraction of 32. So to offset the imbalance that is created, okay, so I'm effectively adding negative 32 at the front, and so I'm going to apply positive 32 at the end. So we have in the rewrite, okay, so we have f of x is equal to negative 2 times the quantity of x squared minus 8x plus 16, okay, and we have negative 36 plus 32. That is going to be negative 4. And you can always go back and check if I were to distribute negative 2 over x squared, you have minus 2x squared. Negative 2 over negative 8x becomes positive 16x. Negative 2 over 16, that will be a negative 32. And negative 32 minus 4 is a negative 36. And now, converting what I have in terms of the vertex form. So I have f of x is equal to negative 2 for x squared minus 8x plus 16. So I have, again, a square trinomial. Now x squared is going to be the square of x. And now how I got to this trinomial. Okay, I had, from factoring, I had x squared minus 8x. And I added 16. And how this came about was from squaring out negative 4 in the completion of the square process. Okay, and that value squared, that's going to be re-entering the scene, and it's going to complete out what we have in the vertex form. So we have for f of x, we'll have negative 2 times the square of x minus 4, followed by the subtraction of 4. And now, regarding whether we have a minimum or a maximum, okay, this is going to be signaled by the leading coefficient in the vertex form. So we have that a is equal to negative 2. And since we have that a is negative, we're going to have the graph to open downward. From the vertex. Okay, so the vertex is going to be the high point. So the vertex is going to be a maximum. If the graph were to be opening upward, the vertex in this case would be a minimum. Okay, now for the values of h and k, now again, we have x minus 4. And I can use this to determine the axis of symmetry as well as the first coordinate of the vertex. So if x minus 4 is 0, we have that x is equal to 4. So we have x equals h is equal to 4. And for what we have in terms of the k value, that's going to be negative 4. So we're going to have for the vertex, vertex hk, so that's going to be 4, negative 4. All right, so just putting it all back together. Okay, so we have first part. Okay, we have addressed the question. Okay, does the function have a minimum or maximum value? This is not a yes or no question. Okay, it's going to be one or the other. Okay, so in this case, because the graph is opening downward, okay, and since the function is one that is quadratic, okay, we have the vertex to be a maximum. Okay, so okay, and where does the minimum or maximum value occur? Notice the x equals sign, and that's going to be your h value. So x is equal to h, and we arrived at 4. And in terms of what's going to be the function's minimum or maximum value, well, for the maximum value, that is going to be the y-coordinate or the k value in the vertex. So you're going to have the function's maximum value is going to be at negative 4, and this is going to occur at x is equal to 4. All right, now through almost the same line of questioning, okay, we have with our next function also one that is quadratic, and we have g of x, where we have 3x squared plus 30x plus 77. And just like what we have with f of x, we're looking at going from standard to vertex form. So again, we have with g of x, okay, so you have 3x squared plus 30x plus 77. And if we look at separating the variable terms apart from the constant, so you're going to have for the variable terms, you have 3x squared and 30x. And just like what we did with -2, we're going to do the same thing with the 3 at the front. So we're going to factor this out and set the stage so that we can do the completion of the square. So we have with factoring out 3. So 3 will go into 3x squared, x squared times. 3 into 30x will go 10x times. Okay, we have followed by the addition of 77. Okay, so again we have the stage set where we can perform the completion of the square. So the first term inside the parentheses is x squared. And I can take the coefficient of the first order term. Okay, so we have 10. And taking half of this coefficient. Okay, so 10 halves is 5. And 5 squared is equal to 25. And so, looking at the formation of the squared trinomial, so we've got 3 times the quantity of x squared plus 10x plus 25. Again, we have plus 77. Okay, now for the activity, again, I have added 25 inside the parentheses. But in the big picture, okay, I'm actually adding 3 times 25. So, in effect, I'm adding 75. So to offset the surplus, I'm going to take 75 away at the end. Okay, so we have in the rewrite. Okay, so we got g of x is equal to 3 times the quantity. So I have x squared plus 10x plus 25, and we have 77 minus 5. Okay, that's going to leave us with plus 2. And again, you can sort of check what we have here to see if this goes back to where we started from. So here we have 3x squared. 3 times 10x is 30x. 3 times 25 is 75. 75 plus 2 is 77. Okay, and so now I'm able to express the vertex form. Okay, so for g of x, I have 3 times. And for x squared plus 10x plus 25, okay, x squared is the square of x. And now for 25, again, the formation of the trinomial after setting the stage with x squared plus 10x. Again, I added 25, and this originated from squaring out positive 5 in the completion of the square stage. So we have 3 times the square of x plus 5, followed by the addition of 2. Okay. And so whether we have a minimum or a maximum, okay, the sign value of the leading coefficient is going to give us the indication. And so we have, so a is equal to 3, and we have the a is positive. And since we have a to be positive, okay, now the graph is going to be opening up from the vertex. And in this case, the vertex is going to be the bottommost point. So this is going to be the location of the minimum. And for the x plus 5 part, okay, if I get the 0 of this, so for x plus 5 equal to 0, we have x is equal to negative 5. Again, that is going to be the h value. And again, just for the k value, we have the addition of 2 at the end. So the k is equal to 2. So for the vertex, so the vertex hk is going to be at negative 5 and 2. Again, the graph opens up, so we're going to have a minimum as opposed to a maximum. So for our first question, okay, we have a minimum. And for this set, notice we have the sequence of the second and third questions to be interchanged. Okay, so if you notice, where does the minimum or maximum value occur? Again, that was the h value we had arrived at. And again, that was at negative 5. So again, x equals h equals negative 5, and k is equal to 2. So x equals h, so you have negative 5. And for the function's minimum value, again, that was the k value, so y is equal to k, and that was at 2. All the other y values, okay, on the graph of this function will be higher than 2. All right, now, yes?
For these equations, can't you use the formula where it's like the fraction is negative and then it's b and then 2a? Because I use that formula and I got the same
That would,
answer.
yeah, if you go with the standard form, there are some books that will stress the standard form more than the vertex form, but both approaches lead to the same destination.
Okay, thank you.
Mm-hmm. Right. Okay. Now for what we have in the case of the third item, okay, so we have looking at solving for w. Okay, and here, okay, we have factors, not completely factored forms, but we can take what we have in the case of number 3. So I'll just say here we have w squared plus 10w plus 24. And we have times 5w minus 15, okay, is equal to 0. And, okay, so we're looking at solving for w, so we got these two factors here. Now, I could technically factor these items further, but we can just go ahead and set up equations with what we have here. Okay, so the first item, okay, we're going to have a quadratic equation. Okay, so you have w squared plus 10w plus 24. Again, we can go ahead and set this to 0. And I can factor this trinomial to w plus 6 and w plus 4. And I can follow through with the zero product property on this. So if I have w plus 6 is equal to 0, we have the w is equal to negative 6. And for w plus 4 equal to 0, okay, so you have that w is equal to negative 4. And for 5w minus 15, if I set this equal to 0, okay, so I can solve for this linear equation and just add 15 to both ends. So for 5 times w is equal to 15, okay, we'll have that w is going to be equal to 3. So it'd be a trio of solutions for W. So one value could be -6, the other value could be -4, and again, just for the remaining possibility, we have +3. So if you plug in any one of those values for W into the equation, then we have equal to 0. All right. Now, for what we have in the case of item number 4, okay, and now, okay, and it says to suppose that the polynomial function f is defined as follows, okay, and it says to list each zero of f according to its multiplicity, and okay, so we're looking at zeros and multiplicities, okay, and I'm going to use this example or this problem as kind of a case for some of the other topics we've looked at, like in behavior, okay, but for what we have at the moment, okay, so you have f of x. Okay, so you have 6x times x plus 9 times, okay, the square of x minus 5, and here times the cube of x plus 11. All right, so we're going to have here, let's see if I can copy this and paste. Okay, so we have here, okay, so we got 6 times x. So that'll be to the first, x plus 9, you have implicitly to the first. And for x minus 5, okay, that would be to the second. And x plus 11, okay, that is going to be to the third power. Okay. Now, for your zeros, okay, so we got okay, so you have with the x factor, 6x equal to 0 or x equal to 0. For x plus 9, you have x is equal to -9. For x minus 5, we have that x is equal to 5. And for x plus 11, okay, now we have x is equal to minus 11. And for what we have in the case of the multiplicities, okay, so we got with 0, this stemmed from the first x factor, which was to the first, so 0 is of multiplicity 1. -9 stems from x plus 9, which is not raised to a higher power, so that multiplicity is at 1. And for 5, this stems from the square of x minus 5, so 5 is going to have a multiplicity of 2. -11 stems from the cube of x plus 11, so that's going to have a multiplicity of 3. Okay, now, and let's say that yeah, see if I'm looking for the end behavior of the graph of this function. Okay, so with what we have in this case now, to determine the end behavior, okay, I'll need, okay, first of all, I'll need the highest degree term. So for what we have from the first factor case, so you have a coefficient of 6. Okay, so for the first factor, okay, you have all of 6x. Now for the binomials and polynomials, okay, if you have those as their own factors, you're going to take the higher or the highest degree term. So we have from x plus 9, we're going to have x. From x minus 5, we have x. And that part is going to be to the second. And for x plus 11, okay, so you got x. And that x, okay, is going to be raised to the third. Okay, so right now we got 6x times x. And x to the second, okay, that's going to be x squared. And x to the third, so we have x cubed. Okay, so here we got 6. X times x is x squared. X squared times x squared is x to the fourth. X to the fourth times x cubed, that is going to be x to the seventh. Okay, so right now, okay, so we got for the leading coefficient, or I should say the coefficient of the highest degree term, so you have 6, which is positive. And for the value of the power, okay, to which we have the highest degree term to be raised, okay, so we have n is equal to 7. So that is odd. Now for the end behavior, okay, so whenever the coefficient is positive and the power is odd, the end behavior is going to be where you have down to the left and up to the right. Okay, and also like in between, if we were to determine where f of x crosses and touches the x-axis, okay, and okay, now for problem 4, we just dealt with the zeros and the multiplicities. Okay, so you got the end behavior. Okay, so you have down to the left and up to the right. Okay, so you got down to the left, up to the right. Now we got the zeros earlier and their multiplicities. And looking at whether the graph is going to cross or touch the x-axis. Okay, so again, if the multiplicity is odd, then the graph is going to cross at that 0. So multiplicity of 1, so you have to cross at x equal to 0. And since negative 9 has a multiplicity of 1, so to cross at x equal to negative 9. And now 5 has a multiplicity of 2, so at x equal to 5, the graph is going to touch at x is equal to 5. And negative 11 with a multiplicity of 3. Okay, again, the graph is going to cross at x is equal to negative 11. Okay, so if we look at kind of a big picture sketch for this function, okay, so we have with our intercepts. Okay, so we got for the zeros. Okay, so you got 0, 5, as well as negative 9 and negative 11. Okay, and now if you've got the origin, okay, to be an x-intercept, well, that's going to be automatically your y-intercept as well. Okay, so we have for the locations and the end behavior. Okay, so the end behavior you have down to the left and up to the right. So setting the stage, so we've got 4 distinct zeros. So you got negative 11, negative 9. We have the origin, as well as 5. Okay, now for the end behavior, you have down to the left. Okay, so you're looking at, okay, just at the extreme end, down to the left, you're looking at down and to the left of x is equal to negative 11. And for up and to the right, you're looking at up and to the right of x is equal to 5. So those are your, what we have at the extremes. Now for what we have in between, so negative 11, the graph is going to cross. Negative 9, okay, the graph is also going to cross. At 0, it is going to cross. But once we get to x is equal to 5, okay, the graph is going to touch. So just for the dynamics of what we have for the graph of f of x, so reading from left to right, okay, so you have like down and to the left, but going now to the right, so I'm going up, crossing, above, and then it's going to descend and cross at x equal to negative 9. And then we have, then it's going to start to rise again. And once we get to the origin, okay, now the graph is going to proceed by crossing. And then it's going to come to a saturation point, and then it's going to fall. And once we get to x is equal to 5, the graph is going to touch, or in effect, it's just going to bounce off the x-axis. And the rest of the behavior of the graph, this polynomial function, is going to be above the x-axis. And again, the extreme ends, we have down to the left and up to the right. All right. Now, for what we have in the case of the next item, okay, so you're looking at, okay, just the basic x and y intercepts. And we have with our polynomial function, okay, so we have, for this in case, you have for f of x, is equal to 2x cubed plus 2x squared minus 24x. Okay, now for the x-intercepts, okay, we're looking at setting y, or f of x, equal to 0. While solving for x. Okay, so you're going to have, again, so you're going to have for setting f of x or y equal to 0. So we have 0 is equal to 2x cubed plus 2x squared minus 24x. And We'll just keep these sides as they are. Okay, so 2x cubed plus 2x squared minus 24x. Now the greatest common factor, we have even coefficients and x in common, so you have 2x, and here we have x squared plus x minus 12. And we can factor even further. Okay, so you got 2x greatest common factor, and for the trinomial factor, we can factor out to x plus 4. And x minus 3. And so setting the stage, so I have 3 linear factors. If I have that 2x is equal to 0, I have that x is equal to 0. For x plus 4 equal to 0, we have that x is equal to negative 4. And for x minus 3 equal to 0, we're going to have that x is equal to 3. Now, if I were to put in coordinate fashion, x equals 0, that's just going to be the origin. X equal to negative 4, you have negative 4, 0. For x equal to 3, I'm going to have 3, 0. And for what we have in the case of the y-intercept, again, we're looking at solving for y as x is set to 0. So we have that y is equal to f of 0. I guess so it's have 2 times 0 cubed. That is 0 plus 2 times 0 squared, also 0. And minus 24 times 0, also at 0. And so we will have for y, okay, that is equal to 0. And so this is just a bit of a repeat. Again, the y-intercept we have, okay, is just going to be the origin. Okay, and just for what we have here, okay, so for the x-intercepts and the y-intercepts, now Alex, okay, is looking at just the main coordinate, not the entire ordered pair. So we have for like the x-intercepts, okay, have x equal to 0, and for negative 4, 0, you can just put in negative 4. And for 3, 0, okay, we had from x equal to 3. So for the x-intercepts, you have 0, negative 4, and 3. And for the y-intercept, okay, we just apply the number 0. So you don't have to put order pairs, just the x values for the x-intercepts and the y value for the y-intercept. So you're going to end up with that particular set. All right. Now, kind of fresh off of what we had looked at regarding end behavior. And we have, for number 6, okay, we have formally addressing this item. And for what we have in this one, okay, so we have for our given function, f of x, okay, so you have the negative of the square of x plus 1 times the quantity of x minus 1 and I'm just going to duplicate this. Okay, so we got so we need the highest order term. Okay, so you got for the negative sign, this will be in reference to negative 1. Now for x plus 1 quantity squared, okay, so you have the higher order term at x. Again, from the expression, okay, you have that x is going to be squared. And for x minus 1, you have just x. So you got negative 1. Now x to the second, that is going to be x squared. And we have times x. So the highest degree term, okay, so that's going to be negative x cubed. Okay. Or just stressing the coefficient, in case you have like negative 1x cubed. Okay, so we have, in the case of the coefficient, so a of n is equal to negative 1. So that's going to be negative, and for the degree n, okay, so that is from the cube of x, so n is equal to 3. So this is going to be an odd power. Okay, now, again, when we looked at the previous situation with n behavior, we had the coefficient to be positive, so the n behavior was down to the left and up to the right. But for this problem, the leading coefficient is negative while the power is odd. So the n behavior, you're going to be having up to the left and down to the right. Or rises to the left and falls to the right. Now, and it says to list each zero according to the behavior of the graph at the x-axis near that zero. Okay, and looking at where the graph is going to cross or touch the x-axis. So this is our part A. Now, again, we have with the zeros. Okay, so we have the first variable factor we have with x plus 1. If we have like x plus 1 is equal to 0, we have the x is equal to negative 1. And for x minus 1 equal to 0, we'll have the x is equal to 1. Now for the multiplicities, okay, now we've got for negative 1, this stems from the square of x plus 1. So looking at the exponent, so that's going to have a multiplicity of 2. X equals 1 comes from just x minus 1, which is implicitly to the first power. And in terms of whether the graph is going to cross or touch the x-axis. Okay, so we have for even multiplicity zeros, those zeros to be locations where the graph is going to touch. Okay, so it's going to touch the x-axis at x equals negative 1. And since 1 has an odd multiplicity value, okay, this is going to cross at x is equal to 1. Okay, so that'll be your part B portion. And part C is just going to be finding the y-intercept. And for the y-intercept, okay, this will be where x is equal to 0. So you have y is equal to f of 0. So you're looking at the opposite sign. Okay, so you've got 0 plus 1 squared times the quantity of 0 minus 1. Now just bring this on down. So we're looking at like negative 1. 0 plus 1 is 1. And it's going to be to the second. 0 minus 1 is negative 1. It's got negative 1. 1 squared is 1. And times negative 1. So the y-intercept is going to be at y is equal to 1. And in coordinate fashion, okay, on the y-axis, okay, so you're going to have 0, 1. Okay, so the y-intercept is going to be at y is equal to 1. Okay, so just taking what we have in the problem. Okay, so if I'm looking at graphing, okay, so again we have two zeros with negative and positive 1. And again, we had the y-intercept at 0, 1. And again, just for the end behavior, again, we had mentioned end behavior was up to the left, down to the right. So just for the projection, kind of a mini projection. Okay, so you have up to the left from the leftmost 0, and down to the right from the rightmost 0. That was at x is equal to 1. And for the in-between activity, okay, so we said that the graph is going to touch at x equals negative 1 and cross at x is equal to 1. So you got touch and to cross. Okay, so if I fill in the gaps, okay, so reading the graph from left to right, okay, so you have touch at x equal to negative 1, so it's going to rise above and it's going to go through the y-intercept. And somewhere along the line, it's going to start to descend and it's going to cross the x-axis at x is equal to 1. And again, you have with your end behavior, you have rising to the left and falling to the right. Okay. And so that would be the behavior, what we have for this particular function. All right. Now, looking at what we have in the case, what are regarded as extrema. Okay, and this is where you have increasing, decreasing behavior, as well as relative minima and maxima. And okay, so it's been a while since we've seen this. And now, in terms of increasing, okay, this is where you have the graph to start sloping upwards. And now, so just looking at what we have here. Okay, so if you notice, like between negative infinity and negative 7, instead of an increase, you have a decrease. Now between negative 7 and negative 5, so you've got negative 7, negative 5, so you have an increase. And between negative 2 and 3, let's see, so you've got between negative 2 and 3, yes, you have that's going upward. So that is going to be in the mix. Now between negative 2 and 6, that's like between x equals negative 2 and x equals 6. So you have like an increase, then a decrease. And even though this relative minimum is above what we started out with, okay, what's going to happen here is that you cannot say that you have an interval of increase if you have a decrease in the mix. So we're going to ignore that. So again, you have between negative 7 and negative 5 increase, between negative 2 and 3 increase only. Now between 6 and 8, okay, have only an increase. And from 8 to infinity, you have just a decrease. Okay, so these will be your three intervals of increase for this given function. And okay, now we have that the function has local minima at which x values. Okay, so for the local minima, those are going to be your dipping points. Okay, so for the minima, okay, you have over here, and this is going to correspond to x is equal to negative 7. So negative 7 is going to be like our lowest x value. Then we have a relative maximum. Then we have another, I should say, local minimum. And that's going to be x equals -2. And we have another minimum. And that's going to be x is equal to 6. And so you have 3 x values, okay, that will have a local minimum, where we have -7, -2, as well as 6. Okay, now for the question regarding the sign of the leading coefficient of f, this is like taking the end behavior parts in reverse. Okay, if you notice, you have up to the left, down to the right. So end behavior, so you have up to the left, and down to the right. And that's going to be indicative of cases where we have that a of n is negative and where n is going to be odd. Okay, so for the sign the leading coefficient right away, okay, that's going to be where we have this to end up as a negative. Okay, and now for the possible degrees of f, again, this goes back to our topic, okay, of turning points. Okay, so this is going to be the combined total of local minima and maximum, or relative minima and maximum. Okay, so for your turning points, we have 1, 2, 3, 4, 5, and 6. Okay, so just coupling with what we have earlier. Okay, so you have the n is odd, and we have 6 turning points. And again, the degree is going to be an odd value that is more than the number of turning points. The degree can never be less than the number of turning points. It's only going to be higher. So if it's an odd value that is greater than 6, well, the only 2 values that will apply in this group will be just 7 and 9. Okay, so again, we can't have 4, 6, or 8 because those are even numbers, and we can't have 5 because that's less than the number of turning points. So we're limited to just 7 and 9. All right. Now, for what we have in the case of the next item, and it says to find a polynomial of degree 3 that has the following zeros. Okay, so we have the zeros of -3, 1, and 0. Okay, so got your zeros. So you have x equal to -3, x equal to 1, x equal to 0. Okay, and we just kind of sort of like going back and kind of working this out in reverse. So you can say that x equals -3 can steal from x plus 3 equal to 0. X equal to 1 we can say comes from setting x minus 1 equal to 0, and we have x equal to 0. So leaving f of x, say, in factored form, and it doesn't matter what order you place the factors, but you can say we have just x plus 3 times x minus 1 times x. Okay, and for the factored form, okay, this is going to be one way that you can express the final answer. Okay, and this might get a little bit confusing. Okay, to say you find a polynomial of degree 3. But the factored form here, even though you don't have any expression to the third power, that's going to take care of itself, because once you get to the expanded form, I'm just going to throw this in. So if I were to multiply x plus 3 and x minus 1, So we have x squared. We got minus x plus 3x, that'll be plus 2x. Minus 3. And if I multiply this trinomial by x, we're going to have x cubed plus 2x squared minus 3x. Okay, and so again, this is just going back to the expanded form. But for the factored form of interest, just this part. And you don't have to raise any of these expressions to any higher power, because once you multiply out, it still comes out to a third degree in the expanded form. All right. Or you could take, like with the degree, the highest order term, like x times x times x comes out to x cubed. So you have automatically degree 3 to be baked in. All right. Now, in the crossover to, once again, polynomial division. Now we have, in this one case, so we're looking at the divisor at 3x plus 1 and the dividend, okay, with this 4-term cubic expression. And if we're looking for the quotient and remainder, so you got 9, so you got 3x plus 1. You have into 9x cubed. Plus 18x squared. We have plus 17x plus 6. Okay, and we don't have any missing degree terms from the divisor or the dividend. And I would like to use synthetic division, but and while we have x in the divisor to be a first order, that coefficient 3, because there's something in front of the x, okay, it kind of throws a monkey wrench in terms of being able to just jump right ahead and perform synthetic division. So we'll just go with the long division process. Okay, so for what we have here, if we look at 3x into 9x cubed, okay, this will go 3x squared times. And for what we have upon distributing, so you got 3x squared times 3x, okay, so this will be 9x cubed. And we got 3x squared times 1, so that would be 3x squared. Again, with log division, we're looking at row by row subtraction. Okay, so 9x cubed will go out. And so the cubes go out. Now for the squares, you have 18x squared. And what's going to be minus 3x squared, so we have 15x squared. And now I'm going to bring down the rest of the terms with 17x and 6. Okay, so I started out taking 3x into 9x cubed. Now I can take 3x into 15x squared, so that will go 5x times. And distributing, so you got 5x times 3x, so this will be 15x squared. 5x times 1, so that'll be 5x. And applying subtraction once again. So you got 15x squared minus itself goes out. 17x minus 5x, and that would be 12x. We have bringing down 6. Now we got 3x into 12x, so this will go 4 times. And distributing 4 over 3x plus 1, so this will be 12x plus 4. And subtracting, so 12x will go out, and 6 minus 4, okay, that is going to be at 2. Okay, and I can no longer continue, for I cannot take 3x directly into 2. So for what we have left over, okay, 2 is going to be the remainder. And the top expression, that is going to be the quotient, whereupon we have 3x squared plus 5x plus 4. Okay. Now, for what we have in the case of number 10, okay, what I'm going to do here, okay, I'm just going to kind of set the stage for how this synthetic division assortment has come to be. Now for number 10, again, your divisor, you have it x plus 3. Now for the dividend, okay, again, you have 2x to the 4th. Plus 10x cubed plus 9x squared minus 7x plus 5. Okay. And again, just for the transition from the long division to the setup regarding synthetic division. Okay, so if I take the 0 of x plus 3, so we have negative 3 okay, and taking the coefficients of the dividend. So we don't have any missing degree terms, so I'm going to go ahead and put down the 2, the 10, the 9, the negative 7, and the 5. And so just looking at what we have now, okay, so with the leading coefficient from the dividend, okay, that would be the leading term coefficient in the quotient. Okay, so we have, so you got 2 is brought down, now we got negative 3 times 2 is negative 6. And 10 plus negative 6 is 4. Okay, so where long division involves row by row subtracting, synthetic division is going to involve column by column addition. Okay, so 2 is brought down, negative 3 times 2 is negative 6. 10 plus negative 6 is 4. Now we have negative 3 times 4 is negative 12. 9 plus negative 12 is negative 3. Negative 3 times negative 3 is positive 9. Negative 7 plus 9 is a positive 2. Negative 3 times 2 is negative 6. 5 plus negative 6 is negative 1. Okay, so we got for the result. Okay, so you got for the remainder is equal to 1. And for the 2, 4, negative 3, and 2, that is going to be for the quotient. Now, the dividend, we had 2x to the 4th, but with the 2 brought down, a degree is given away. So this 2 becomes 2x cubed. 4 will be in reference to 4x squared. Negative 3 will be in reference to negative 3x. And we have finally 2. Okay, so these will be the terms. Now, for these squares here, okay, there are too many terms, especially for the first square, to put in all this stuff. So for what we have in the case of the ratio, so kind of a long statement. So for the first part, okay, you got your quotient. So you have 2x cubed plus 4x squared minus 3x plus 2, and see the remainder, that is negative 1. So that's going to be plus negative 1 all over x plus 3. Okay, so you got the 4-term expression applied to the first square, negative 1 for the second in the full display. All right, now in the case of what we have regarding remainder theorem. And we have for number 11, okay, it says here to use the remainder theorem to find p of 2 for this particular polynomial function. And it says to give the quotient and the remainder for the associated division and value of p of 2. Okay, so okay, now you could use the remainder theorem, like if you find like the remainder is going to be p of 2, so you plug in 2 for x, so looking for the value of p of x whenever x is at 2. But since I'm looking for the quotient, I'm just going to go with the synthetic division route. Okay, so we have, in this particular case, right, so you have, again, so you got p of 2 for p of x equal to x to the 4th minus 2x cubed minus 5x squared plus 3. Okay, and we're looking at the remainder is equal to p of 2. Okay, and so if I'm setting things up like along the lines of synthetic division, okay, so again got p of 2, so your input is x is equal to 2. Okay, and you can say this is going to originate from having sets equal to 0, x minus 2. And I'm just going to mention now, just from the long division setup terms, looking for the quotient and the remainder. Just want to mention, okay, so with the polynomial dividend, we have x to the 4th minus 2x cubed minus 5x squared. Okay, now we don't have a first order x term, so we're going to apply a 0 placeholder. And we finally have plus 3. And again, just for what we have in synthetic division terms. Okay, so the 0 of x minus 2, okay, still have at 2. And again, just for the coefficients of the dividend, so you have 1 for x to the 4th, negative 2 for x cubed, negative 5 for x squared, 0 for the missing x, and 3 for the constants at the end. Okay, so with synthetic division, so I can bring down 1. 2 times 1 is 2. Negative 2 plus 2 is 0. 2 times 0 is 0. Negative 5 plus 0 is negative 5. 2 times negative 5 is negative 10. 0 plus negative 10 is negative 10. 2 times negative 10 is negative 20. And 3 plus negative 20 comes out to negative 17. Okay, so we have, in this particular case, right, so we got for the remainder, so the remainder would be p of 2, which is equal, okay, to negative 17. And just for the terms making up the quotient. Okay, so if you notice, okay, we had x to the 4th, but after the round of synthetic division, this one is now in reference to x cubed. Notice the 0 here. So we're going to have a missing x squared term. Minus 5 will be in reference to negative 5x, and we have minus 10. And so for the quotient, okay, so for the quotient, we don't have an x squared term, so this will be without zeros displayed. We'll have x cubed minus 5x minus 10. So again, the quotient we have x cubed minus 5x minus 10. And for the remainder, okay, again, that is p of 2 is equal to negative 17. All right. Now, in terms of what we have looking at the factor theorem, and this is binary. If the remainder is 0, then the expression is a factor. If the remainder is not 0, then the expression is not a factor. Okay, so we got for this one, okay, if I use the factor theorem, okay, and what I can do, I can just go ahead and set this up in terms of synthetic division. I'm going to do a little bit of a shortcut here. So you got p of x, you have x cubed plus 4x squared minus 9. Notice we have a missing first order x term. And for x plus 3, x plus 3 is equal to 0. And to translate what I have in terms of synthetic division, okay, I can use the 0 of x plus 3. Okay, so you got negative 3 in reference to x plus 3. Now for p of x for the dividend, so you got 1 for x cubed, 4 for x squared, 0 for the missing first order x term, and negative 9 as the constant closes out the dividend expression. So if we look at what we have, okay, through the lens of applying synthetic division, okay, so 1 is brought down. Now we have negative 3 times 1 is negative 3. 4 plus negative 3 is 1. Negative 3 times 1 is negative 3. 0 plus negative 3 is negative 3. Negative 3 times negative 3 is positive 9. And guess what? Negative 9 plus 9 is 0. So the remainder is going to be p of negative 3 is equal to 0. So in terms of filling in the blanks, okay, so p of negative 3 is equal to 0. And since there is no remainder, that means that we are going to have x plus 3 to be a factor of this polynomial expression. So p of negative 3 is equal to 0. And once again, x plus 3 is a factor. All right. Now, for what we have in terms of rational functions, and we have for number 13, okay, now we got two rational functions, f of x and h of x, and we're looking at which of the graphs will be the best fit for these rational functions. And we have, first of all, so you have f of x equal to 3x plus 6. All over x squared plus 2x minus 8. And now this rational function is already going to be in simplified form, but I'm just going to express in factor terms. So you got x squared plus 2x minus 8. Now this would factor out to x plus 4 and x minus 2. Okay, now technically, okay, so x plus 4 cannot be 0, and x cannot be negative 4, and we have that x minus 2 cannot be 0, so we have the x cannot be equal to 2. Okay, so we have with these items, okay, if you notice, neither x plus 4 nor x minus 2 will cancel out since we don't have anything about these in the numerator. Okay, so we have, in effect, okay, we want to have, because x plus 4 and x minus 2 remain, and we have our vertical asymptotes to be x equal to negative 4 and x equal to 2. Okay, so these are vertical asymptotes. So if we look at kind of doing a process of elimination, okay, to see what has x equal to negative 4 and x equal to 2 and what doesn't. Okay, and if you notice, we have for graph A, okay, we don't have x at negative 4, x at 2. So graph A is not going to belong right now, negative 4, 2. Graph B has those, so does C, negative 4 and 2, yep, in graph D, but graph E, as well as graph F, we don't have those vertical asymptotes. So A, E, and F go out, and so we have B, C, and D in the running. Now for degree comparisons, again, for the numerator, we have from x, we have n is at 1. From the denominator, we have x squared, whereupon we have the m is equal to 2. N is at 1, m is at 2, so n is going to be less than m. So we're going to have a horizontal asymptote at y is equal to 0, or namely the x-axis. And I believe that B, C, and D have the same horizontal asymptote. So we've got these asymptotes, the vertical and horizontal, are common to graphs B through D. But graph F cannot be all three of these. Okay, so in terms of any tiebreaker, a common one that will be used, okay, so especially among graphs that will have the same asymptotes, we can determine what the y-intercept is. Now for this rational function, so for the y-intercept, we had that y is equal to f of 0 so we got 3 times 0 plus 6 all over 0 squared plus 2 times 0 minus 8. So you have 6 over negative 8. So for the y-intercept, okay, that's going to be a negative amount, which you will have with minus 3/4. And in coordinate terms, on the y-axis, okay, we have 0, negative 3/4. Okay, so looking at what we have among these three graphs, okay, so looking at where we have a negative intercept on the y-axis. If you notice, okay, we have for B, okay, now negative 3/4 to be here, and this middle section of graph B is not coming close to that. Graph C, again, you have that section above the x-axis, so that's going to go out. And for graph D, okay, notice, okay, we have about negative 3/4 along here, and graph D is running through this along the middle portion. So in terms of like which is going to be the graph of the function f of x, it turns out that it will be graph D. Right. Now, for what we have in the case of h of x, okay, so you have 8 over x squared minus 2x minus 3. So just hitting the reset button, since we're working with the examination of these graphs. So D is going to be for f of x. So basically for h of x, you're looking at A, B, C, E, or F. So we have here, so we have for h of x, let's see. Okay, so for h of x, we have 8 all over x squared minus 2x minus 3. And just like f of x, okay, this is already going to be in simplified form. So just writing in factored form, we have 8 all over the product of x plus 1 and x minus 3 again for the function to be defined, neither x plus 1 nor x minus 3 can be 0. So if x plus 1 cannot be 0, x cannot be negative 1. If x minus 3 cannot be 0, we have that x cannot be at 3. And guess what? Neither x plus 1 nor x minus 3 will cancel out. And these exclusions will be the vertical asymptotes. So you have x equal to negative 1 and x equal to 3. And we'll go ahead and look into the horizontal asymptote. So for what we have in the numerator, okay, there's no x term. So we have that n is equal to 0. And in the denominator, okay, so you got m is equal to 2. And for how the values size up, okay, we have that n is less than m So we have a horizontal asymptote, y is equal to 0. So you got 3 asymptotes, 2 vertical at x equal to negative 1, x equal to 3, and a horizontal asymptote at y is equal to 0. So looking at what is present now, so you got negative 1, 3, 0. A is in the running. B, this is not, got the wrong vertical asymptotes. Likewise with C. And again, D was already for f of x, negative 1, 3, 0, negative 1. Okay, so it comes down to graphs A, E, and F. And looking at what the tiebreaker is going to be. So, and chances are, before we're able to get to the tiebreaker with the y-intercept, see how this is going to come out. So we have for the y-intercept, we have y is equal to h of 0 So we have 8 all over, and we have 0 squared minus 2 times 0 minus 3. You have 0 squared is 0, minus 0 is 0, minus 3. So you have 8 over negative 3. So there's going to be a negative y-intercept. So we have at 0, negative 8/3. And to see what we're going to have, okay, so for graph A, yeah, it looks like we have, yeah, so you got negative 1, negative 2, negative 3, so you have negative 8/3. Graph E, guess what? We got that portion above the x-axis, so E goes out. Same thing for graph F, you're not even remotely close to negative 8/3, and that section is just above the x-axis, so F goes out. So for what the result is going to be for the graph of h of x, okay, this will come out to A, right? And now for what we have in terms of looking at, okay, the asymptotes and the intercept, and we have for this remaining set of items, okay, so we have for f of x, now we got 2x squared plus 2 all over x squared minus 2x minus 3. And this ratio will also be in simplest form, but I'm just going to go ahead and factor. For x squared minus 2x minus 3. So we got with our factors, see we have x plus 1 and x minus 3. Again, if x plus 1 cannot be 0, so we have that x cannot be negative 1. If x minus 3 cannot be 0, we have that x cannot be 3. Okay, so again, since neither x plus 1 nor x minus 3 are factors in the numerator, those are going to remain. So we have two vertical asymptotes with x equal to negative 1 and x equal to 3. And see if we have any other asymptote. Okay, so for what we have in the numerator, okay, so we got the x squared. So n is equal to 2. I also have second degree nx in the denominator, so I have the m is equal to 2. And so n is at 2, m is at 2. And this time we're going to have that n is equal to m. And this is going to signal that we're going to have a non-negligible horizontal asymptote. In fact, this will be the constant that results by taking the ratio of the highest order terms in the numerator and denominator. So we have 2x squared from the numerator, x squared from the denominator, and so we want to have that y is equal to 2. So for what we have in the mix, okay, so looking at our asymptotes, okay, so we got x at negative 1, x at 3, y at 2. Okay, so it looks like x at negative 1, x at 3, y at 2. So it looks like that is in the running. Graph B is not. And C does not have the right horizontal asymptote. Got negative 2. Nope. Graph D. Graph E, no. And graph F, yeah, so we got -1, +3 for the vertical, +2 for the horizontal. So it comes down to graphs A and F. And it looks like the tiebreaker is going to be with the y-intercept. And whether it's going to be positive or negative. So you have f of 0. This is going to be 2 times the square root of 0 plus 2 all over 0 squared minus 2 times 0 minus 3. Again, so you got 0 plus 2 is 2. And we got 0 minus 0 minus 3. So that's going to be negative 2/3. And on the y-axis, okay, so we have the coordinates 0, negative 2/3. And so between, okay, so you have 0, negative 2/3. It looks like it's going to come right here, whereas it won't in the case of graph A. So graph A is eliminated. So for the graph of this function, f of x, okay, this is going to be f. And for what we have for g of x, okay, so for g of x, okay, so you have 2x minus 2 I believe that was x squared minus x minus 6. And if I go ahead and express this in factored form, so the numerator we have 2 times the quantity of x minus 1. And for the denominator, we have x plus 2 times all of x minus 3 so for x plus 2, okay, that cannot be 0, so x cannot be negative 2. And x minus 3, that cannot be 0, so x cannot be 3. Okay, so negative 2 and 3 cannot be on the graph of g of x. However, since x plus 2 and x minus 3 will not cancel out, okay, those are going to be our vertical boundaries. So you have the vertical asymptotes with x equal to negative 2 as well as x equal to 3. And we can go ahead and see if there are any other asymptotes. Okay, so we have with 2x minus 2, okay, so we have x will be a first degree into 2x. So you have the n is equal to 1. And from the denominator, okay, we have from x squared, we have the m is equal to 2. And so we're going to have the n is less than m. So we're back to where we had the horizontal asymptote is going to be the y-axis from x-axis. So you have the horizontal asymptote at y is equal to 0. Okay, so looking at what we have here, we got 3 asymptotes with x at negative 2, x equal to 3, and the x-axis with y is equal to 0. Okay, so you don't have the right, got negative 2, so graph A doesn't have it. Graph B doesn't have it. It's got the negative 2 and 3, but you don't have y is equal to 0. C does not have it. Looks like D is in the running and E is in the running, and so it's coming down to these two graphs. D is going to have a positive y-intercept. E is going to have a negative y-intercept. So once again, it's going to come down to the sign value of the y-intercept for g of x. Okay, so you have g of 0. Okay, so you're looking at 2 times 0 minus 2. All over 0 squared minus 0 minus 6. And 0 minus 2 is negative 2. And we have minus 6. And negative 2 over negative 6 comes out to a positive 1/3. So between graphs D and E, okay, so for the one that has the positive y-intercept, it's like it's going to be this one, whereas E has a negative y-intercept, so you cannot have 1/3 on that one. So for the graph of g of x, okay, this will come down to D among the 6 choices.